Okay, hello everyone. So this lesson is going to be asynchronous, meaning this is a homework lesson that we'll then work on in class, and I'll answer any questions you have about this in class. And yesterday you created your own number system using circles and squares, and we're going to continue to think about ways we can communicate using only two symbols. And is there a limit? Can we if we're just thinking of the number of answers we could have, or even just a number, are we limited when there are only two ways that a device can answer? And that's what we're going to go to today. This is the first time we're going to be learning about binary number systems, okay? And how they work. So here we have, when you only have one place value, which, in our number system, we're talking base 10, tens, hundreds, or ones, tens, hundreds, thousands, 10,000s, 100,000s. So here we're talking about one place value. With one place value, we can only have two possible patterns, a square or a circle. Okay, so if let me just click on this. Okay, so if we think of one place value, but two possible patterns, you have a circle and a square. I started with the circle, but I could have just as easily started with the square instead. So if I have two place values, there are four possible patterns. I can have, so this would be the first place value, and this would be the second place value. If I have three place values, there's 8 possible patterns. Okay, we're going this way. And really what you're doing is you're just trying to figure out all the different combinations, but this should, as yesterday, it should follow some rules, right? Okay, instead of 2 shapes, what if we had 10 shapes? This is going to seem much more familiar to you. They're just shapes, right? We're used to believing that these have some significance, but it's just because our experience is that this represents a 0 and a 1 and a 2. But if we go back to 2 days ago and we were thinking about all the different ways to represent 7, the number 7, this is an arbitrary shape. We just happen to know what that means, right? So 2 places equals 100, 2 shape patterns. Okay, and then so it's from 0 all the way to 99. We understand this, right? Because you have 10 possible choices. You have 10 possible choices in the ones place before you have to roll over and add a 1 to the tens place. So what you need to be thinking about is that when you're dealing with binary and you only have 2 shapes, you have 2 shapes you can have in the one place value, and then once you've exhausted those 2 shapes, you have to go to the next place value. And then once you've exhausted those 2 shapes, you have to go to the next place value. Okay, so when we are thinking of base 10, what we're very familiar with, what happens when we count up to the last shape? So we get to 99, and then what happens next? We've exhausted our 10 digits, right? We have from 0 to 9, that equals 10 different shapes. And once we've exhausted them here, we have to start over. These will become both zeros, and this becomes a 1, as we know, right? And then we know that the 100 comes next. When we run up to the last shape at 9, right, we roll over back to 0 and add 1 in the next place to the left. This is the place value that we have when we have used that we've used all our lives and we're most familiar with. Okay, so where are we going with this? Binary, where we only have two shapes, 1 and 0. Binary is a number system with two shapes. Right? A bicycle has two wheels. Okay, so we have a 0, a circle, and a square. And they're going to transform, and now we're just going to think of it as a 0 and a 1. Okay, so when we think of organized lists, here what we have is we have zeros, and where we have circles, they're turning into zeros, and where we have squares, we're going to make them ones. Okay? And instead of shapes, that's just what we're going to be thinking of. So, if we consider the ones to be ones, right? And we go through, we have 0, 0, 0, so this would be a 0. And then we have 0, 0, 1, that's worth 1. If we now say that in this place, right, it's either going to equal 0 or 1, and we're in base 2, now I want you to think about this compared to base 10. Every time in base 10 you go to the next place value, it's times 10. But every time you go to the next place value in base 2, it's times 2. So here, let's look here. This is either going to be a 2, or if we put a 0, it's going to be a 0. So this is worth 0, this is worth 2, this is worth 0. Add them together and you get 2. Here, this is worth 0, this is 1, this is 1, and we know the 1 in this place is not times 10 as it is in base 10, but this is times 2. So 2 plus 1 is 3. And then here, we go to the next column, and it's times 2 again, because again, we only have 2 shapes. And in base 10, we have 10 shapes. So here we have, this is worth 4, 0, 0, 4, 5. This is worth 4, 0, 1. Here, this is worth 4, this is worth 2, this is worth 0. Add them together, you get 6. So hopefully you're getting the idea of this. For today's activities, you're going to be creating your own Flippy Do. This is what I've handed you in class. This is a tool that will allow you to quickly and easily translate between the decimal base we are used to as humans and the binary base that computers use. Okay, so I also am going to share with you a digital Flippy Do. So you're going to fill it in. 2 to the 0 power, anything to the 0 power is 1. I know it looks like a 7, but it's a 1. 2 to the first power is 2. 2 to the second power, 4. 2 to the third power, 8. 2 to the fourth power, 16. That's not a 76. 2 to the fifth power, 32. 2 to the sixth power, 64. 2 to the seventh power, 128. And they just double. Okay, 1, 2, 4, 8, 16, 32, 64, 128. And then on this line, you're going to have all zeros, and then you're going to flip it up, and you're going to put ones. Okay? Okay, each place value represents one bit, which is short for binary digit. Binary digit can be a 0 or 1. Okay, and your Flippy Do has 8 bits. And just so you know, going forward, 8 bits equals a byte, B-Y-T-E. Okay. Go through this animation. Okay, 1 byte is 8 bits. So each place value is a bit. Okay, so now you're going to work through your Flippy Do. Try this out. Try out your Flippy Do. represent these decimal numbers in binary. So you're going to take out your Flippy Do and you're going to flip up the numbers that will flip up. Either you're going to put a 1 or a 0 in your byte, okay, and to the left you could have all zeros, and then you're going to see if you can represent 7. See if you could represent 20, okay, and then you're going to flip your Flippy Do to this and count it and see what they equal. You should be hitting pause now and doing these, and then coming back and I'll show you the answers. And the thing to think about, let me just go back. The thing to think about in your Flippy Do is that, so for the number 7, right, you're going to show a 0. Let's pretend the number's 10 because that's not one of the questions. But you're going to put a 0, a 0, a 0, a 0. So 8, so you're working from left to right. 8, you would put a 1. How much value is left to get to 10? So this would be a 1. Well, I can't put a 1 here because that would represent 4 and that would give me 12 and that's too much. So it would be a 1, a 0, plus 2 would get me to 10. So I'm going to put a 1. I don't need any more, but I do need to put a 0 here as a placeholder. So 1, 0, 1, 0 represents 10. So if we go back here to the 7, how do you get to 7? Again, you're going to start left to right and do the same thing. Hit pause, please. And let's continue. Okay. Hopefully you really hit pause, and here is the answer for this. Here are the answers for these. If this doesn't make sense to you, now is absolutely the time to hit pause and go back and work with your Flippy Do until you understand this, and definitely reach out to me if you do not understand how we arrived at these numbers. Okay, so on your Google Classroom, you have this activity guide. You're going to work with your Flippy Do to complete this activity guide. Just so you know, you're going to continue down using 4-bit numbers, and you're just going to do 0, 1, 2, 3, 4, 5, 6, all the way until you get to whatever this brings you to, and the same thing here. Okay, so you're going to work and answer these questions. This is, I just want to enlarge this, fill in the binary equivalents for the decimal numbers below. We've started you off. So the decimal numbers are what will drive this. So you'll fill in this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and then down here, what you'll do is, this says complete the chart with 8-bit binary, and you'll notice there's a space. The space doesn't mean anything, it's just so that visually you can read it more easily. 8-bit binary numbers that are exactly 1. We've done the first one for you. So what this is asking you to do, if you notice, the 1 here is all the way to the right, and then it moves 1 more place value to the left, and now it's 2 place values to the left, and it's just going to keep moving its way all the way to the left, and you're just going to write binary numbers that have 1, 1 in them. Okay, so we're going once again to compare the decimal. Deci means 10. December used to be the 10th month. Out of our months. That's why December is, and Sept means 7, and Oct means 8, but then you had Julius Caesar and Augustus Caesar, who were egomaniacs, and they had to throw in July and August as months, and so it pushed all of these months that actually made sense as far as being associated with numbers. It pushed them out of sequence. Okay, so here we have base 10, you're dealing with 10 possible shapes, binary, two possible shapes. We're